how can we start with neutral water and wind up with negatively charged substance? So we were looking for a positive charge as well. And we found it just beyond the negatively charged exclusion zone.
This is starting to sound like a battery.
Yeah, exactly. You got a battery.
Greetings to the brightest audience in the country. This is Real Science Radio. I'm Fred Williams.
And I'm Doug McBurney, Bible student, science geek, amateur comedian. Fred, it is great to be back with you talking about real science on Friday.
So today we have a special guest who has some real interesting research that revolves around water. When I watched the presentation on this, I was blown away, and I'm sure you will be too, on things that you really likely never knew about water. You know, such as, for example, its role it plays in the cell. It acts as a battery. I mean, there's so many fascinating things about water. And we have the great honor of welcoming to the RSR airwaves Dr. Gerald Pollack. Welcome to the show, Gerald.
Oh, I'm really happy to be with you. Thank you for the invitation.
Well, awesome. Dr. Pollack maintains an active laboratory at the University of Washington in Seattle. He's the founding editor-in-chief at Water, a multidisciplinary research journal, executive director of the Institute for Venture Science, co-founder of the Fourth Phase, Inc., and founder of the annual conference on the physics, chemistry, and biology of water. He has received numerous honors, including the Prigogine Medal for Thermodynamics, the University of Washington Annual Faculty Lecturer, the NIH Director's Transformative Research Award, and the first Emoto Peace Prize. He is recognized internationally as an accomplished speaker and author. Did I pronounce everything right? Because a couple of those things I wasn't sure. How did I do?
I think you did pretty well.
All right. Now, before we get to...
Prigogine usually doesn't get pronounced correctly, and I'm not sure that I'm pronouncing it correctly.
Okay, that's the one I was worried about. So it makes me feel better that maybe nobody knows. And it's one of those things that it depends on if you're from New Jersey or from Miami or from LA on how you want to pronounce it.
Or from Belgium.
All right.
Yeah.
Oh, there we go. Now, before we jump in, not to be funny, but before we jump into the water, we want to dive into our interesting fact of the week. Fred, please, I'm on the edge of my seat. Lay it on me. The interesting fact of the week.
Okay, here it is. The interesting fact of the week, Doug. Over 90% of the world's supply of fresh water is located where?
What was the percentage?
90% of the world's supply of fresh water is located where? On the globe.
Well, you know what? I've never thought about that. I'm going to say the Great Lakes.
Not a bad guess. So, Doug, I'm going to give you a clue. We did a show recently on this area of the globe, just last week.
Antarctica.
There you go. Okay, so.
I'm not sure if you guys are aware, but there's so-called primary water, which exists down around the mantle of the Earth, and it's been estimated that the amount of water there exceeds what exists on the surface of the Earth by a factor of maybe 3 times, including all the oceans. So there's a vast supply of water, and nobody knows whether it's entirely drinkable or not drinkable. It remains to be seen. But there is that source of water that exists down there.
Oh, interesting. Is this I've read articles about water that is, it seems like it's impregnated into material. I don't know if you call it rock.
Yeah, absolutely. Yeah, some of it is. There's not so much that's known about it because I guess there's not too much money that's going into research. But potentially, this could be a huge source of drinking water beyond Antarctica if it melts.
Wow.
Yeah.
Okay. So that was news to me, Fred, that Antarctica is fresh water. I did not know that. You see, you live on this planet for all these years and you think you know stuff, and then you find out that there's relatively simple, obvious, big things that you don't know. So Keep paying attention, folks. That's the lesson.
And I did say the globe because there's actually more fresh water in the atmosphere than all the rivers combined on the planet. So, anyways, I want to get into an aspect of water that, again, that many of our listeners, likely most, if not all, have never heard. And so that's why we brought you on the show, Dr. Pollack. So can you give us maybe a thumbnail sketch, start out on what you found with researching water?
Sure, absolutely. Well, I guess it all starts with a chance meeting of a guy named Gilbert Ling. This was in Hungary, and Gilbert Ling came from China, and he was you might say, young, distinguished scientist. They looked throughout China to pick 3 people after World War II to come study here, and they picked a physicist, a chemist, and a biologist. And Ling was a biologist. The physicist went on to win a Nobel Prize, and my Chinese student said that the chemist also went on to win a Nobel Prize, and Gilbert Ling, for what he did, should have won at least 2 Nobel Prizes. Anyway, he was in a distinguished cohort. So I met him, and he was presenting the idea that inside the cell, that the water was not like liquid water, that it was structured, which means, as he was describing it, that the molecules were lined up like soldiers at attention. I was mesmerized. I heard not only the presentation of Gilbert Ling and a whole batch of evidence to support his point of view, but also from 10 or 12 other people who had been invited, who also had evidence to support that point of view. So I came home from Hungary, and I'm easily enchanted by interesting ideas, and I don't trust myself. So I asked my students, some of my students, to read one of Ling's books and get back to me. And they got back to me. They said, "This is amazing. This stuff, if it's true, it means that all of biology is wrong, because one of the prime assumptions in biology is that the water is like liquid water inside the cell." And Ling said, no, it's not like that at all. I was can't resist, something like this.
Well, Dr. Pollack, I don't want to interrupt, but he used the words, "all biology is wrong." That's a pretty brash statement to make.
He was a brash guy. He was not known for his diffidence. He was right out there. No.
Oh, wow! So I want to hear. I want to hear about this, because a statement that big, well, I need to know what this is all about. But I got to apologize to you off the top, Dr. Pollack. I was told we were interviewing the songwriter behind Cool Water, performed by Marty Robbins in the 1960s, and that he had also written Gimme Some Water, but by Eddie Money in the 1980s. And I found the timing of all that to be pretty hard to believe. So, but what you just said is even harder to wrap my head around. All biology's wrong. Water is structured. Are you saying? What do you mean?
Well, I mean, okay. So what the textbook says, what's going on in the cell, is that molecules are diffusing around. Now, for example, enzyme and substrate, in order to make a reaction occur, the two need to move around and get close to one another. Now, if the water inside the cell is structured, as Gilbert Ling said, it's kind of like ice, but not ice. But because in ice the molecules are not moving at all, or hardly moving, and so if you insert something in ice, they can't move around. You see, and so one of the most basic presumptions in all of biology is that molecules are able to move around and diffuse and whatever. But according to Gilbert Ling, that shouldn't be possible. So that's what I mean by all of biology is wrong. Maybe all is an exaggeration, but it comes pretty close to it.
Well, so if the water in the cell isn't liquid water as we know it, did Gilbert Ling tell us what it was?
Well, he told us what it was, and what we found when we started to do experiments is that thematically he was correct, but he wasn't correct in all of what he was espousing. And we found, as you said, like a battery inside of water. So let me explain. Gilbert was suggesting that the water is structured. So each molecule, you can think of a water molecule as a dipole. That's a bean with a plus at one end and a minus at the other end. So here's a bean, and so you got plus and minus. Next bean, plus and minus. So the minus end will stick to the plus end, and you can stack these. Okay, and it's like a crystal. Crystals, and in crystals, the atoms or molecules are organized. And so we started our experiments thinking, okay, there's a crystal somehow, and we got to identify that crystal. So how do you identify the crystal? Well, we knew that the exclusion phenomenon, that if you, for example, if you start with water that's contaminated, it's got junk in it, and you want to freeze it to ice, and the ice crystals are pure. So you have to get rid of the junk in order to attain purity. And that's pretty much what we were looking for. So we took a chamber with water and particles, microspheres, which we had hoped we would see some kind of exclusion of them, and we plunked into that chamber a gel. And we looked in the microscope, and what we found next to each and every surface of the gel is that those microspheres are getting pushed out. It took about 2 or 3 minutes, and so we saw what we began calling an exclusion zone. Easy to remember. That works. So, and that zone is like a crystal because it pushes out. It's ordered. Okay. So we wanted to find out more about the kind of ordering. That demonstration, all it did was show that there's some kind of order there, but it didn't say much about it. Later, we performed many experiments, and we found that every feature of this water that was in the exclusion zone differed from liquid water. And so we began calling it fourth phase water. That is, we know water has 3 phases, a solid, liquid, and vapor, and this appeared to be a 4th phase. And that's the basis of the title of my book, which has become really popular.
Dr. Pollack, before you go on, did you introduce some energy, or what did you introduce to cause the water to do this?
Well, we didn't introduce the energy, but the energy turned out was there. It was there all the time. We just didn't notice it. Let me get to that in a moment.
Wow.
The energy, because the energy is really critical. So we started sticking electrodes just for fun in that exclusion zone, the zone that pushed out the particles, the microspheres. And I had some experience with the tiny electrodes, and we found that that region was negatively charged, was not neutral. We started with neutral water, and out of the neutral water came this zone, like maybe 1/4 of a millimeter thick, which by molecular standards is really huge. And it was all negatively charged. It wasn't always, there were some exceptions to that negative charge, but by and large, especially biologically, it's negatively charged. And that didn't make any sense because we start with neutral water. How can we start with neutral water and wind up with negatively charged substance? So we were looking for a positive charge as well. And we found it just beyond the negatively charged exclusion zone.
This is starting to sound like a battery.
Yeah, exactly. You got a battery, so you got a negatively charged zone. And next to it, you got a positively charged zone. So it meant that the water had transitioned into separated charges, negative and positive. Just like the first step of photosynthesis. The first step is water gets separated. And by the way, water gets separated by virtue of the energy from light. Now, we should have known that clue about the energy. To create a battery or charge a battery, you need energy. You can't create energy out of nothing. You can only translate one kind of energy into another kind of energy.
Exactly.
Yeah, like a light bulb, electrical energy gets translated into light energy and heat energy. So,
Right.
so we were wondering where the energy came from, and to do this, and to our great surprise, as a student who either he was bored or he was curious, I don't know, he was doing the same experiment that I was telling you about, plunking a gel or other polymers or molecules into this chamber with microspheres and water and see that exclusion. So he was doing the same experiment, and he never told me whether he was curious or bored, but he saw a lamp sitting next to one of those gooseneck lamps. You could bend it and twist it every way. He takes the lamp and shines it on the chamber, and he calls me in to show me the result. And where the region was illuminated, the exclusion zone grew enormously, like a fat, not 5%, but like 3 times, 4 times. I was astonished.
Yeah. So for our radio audience, we're showing a video clip of this example that Dr. Pollack is talking about, how this light as an energy source is making this EZ zone expand.
So immediately it became clear it's light, just like the first step of photosynthesis. And of course, we wanted to find out what wavelength of light. A light bulb contains an array of wavelengths ranging from at the very short end, ultraviolet, and then visible light, and then infrared at the long wavelength end. So we tested in the laboratory with bona fide experiments, not the object of curiosity of a student, but he's the guy who discovered it. Which wavelength? It turns out ultraviolet, nothing. Visible light, maybe a little bit, especially toward the reds, and infrared, enormous impact. Even a very, very small, a very weak light-emitting diode emitting infrared could expand the exclusion zone by a factor of 10. We found.
Oh my goodness! Wow.
Yeah.
Huh.
So I guess your question is probably, well, okay, infrared, but where do we find infrared? I know, in the toaster we push down the bread, and the coils light up and glow. And
I think my TV remote. I could shine my TV remote, right? I think that's infrared, if I remember.
Okay, well, there you go. But a lot of people are not so experienced as you. They press it all the time, but they never think about it. But if you want to actually test to see where the infrared is coming from, it's not just the coils in the toaster or the oven or the sun, which is the primary source, because roughly half the energy coming from the sun is infrared energy. That's why it feels warm. But if you were to turn off all the lights, even the real science radio, which I see, and it's
even turn off our neon sign there.
Yeah, turn off everything. If you turn it off, and you can't see anything, and your cell phone camera can't record anything, and you whip out your infrared camera, which is just like an ordinary camera, except the sensor is sensitive to infrared wavelengths and not visible wavelengths. So even if it's completely dark, you get a beautiful image of everything, and everything around. That's why the military uses it at night. Check out the enemy's tanks.
Yeah.
Yes. Yes.
The listener can try this at home. You can take your camera and get your TV remote, and you'll see that infrared light coming out of it if you look at it with your camera.
So that's how the night vision goggles that the Army has, that's how they work.
Yeah, that's how they work. Yeah.
So, like, everything is giving off some infrared
Everything,
energy?
It absorbs light from the sun and re-radiates that light, often in the infrared region. What that means for us, what it means is that the energy that you need for building easy water is all around us all the time. If you expose it to the sun, you get more of it. Or if you jump into a sauna, that heat is basically infrared energy. You get more of it, but the energy is there, which means that wherever you have the right surface, I said, I talked about gel surfaces, polymer surfaces, biological surfaces. They need to be so-called hydrophilic, which means water-loving, and most surfaces are like that. So if you have that situation, and you have water, and you have the energy, that water will automatically turn into fourth phase or easy water, and it's a battery. And so this is a radical change from everybody's thinking, because we've known, and I put quotes around known, since 1941, when a scientist named Lippmann found that the energy comes from the molecule called ATP. It's in every textbook. It's for generations, and I guess you'd be hard-pressed to find somebody who doesn't believe it. However, there are several papers that were published subsequent to that, which argue that it's wrong. And one of the papers I know pretty well, because I know the two people who were the authors, because they were or are in the muscle field, which is my previous field. So I know these guys, and they studied this carefully, because in muscle contraction, you really want to know what's the source of energy for muscles to contract. And they found that there's nothing that's unique or unusual about the phosphate bonds in ATP. The idea that came from the studies of Lippmann were challenged, but almost nobody has paid any attention to those challenges. So the truth is, we don't know whether the energy that propels us, to run the marathon, does it really come from ATP or does it not? Because the evidence is equivocal on that. Well, there's another possibility, and the possibility is that the energy is electrical energy, the kind of battery, because our cells are filled with this stuff, filled with easy water, and so if the cells are filled with easy water, they're filled with basically a battery, with batteries, and these batteries can supply energy. And we actually confirmed in an experiment published just a few months ago, we found directly use of this energy.
So the fact that you're enlightening us that there are challenges to the ATP energy model, and you're also bringing up tangentially one of our favorite subjects, is that whenever there are significant challenges like this, they tend to be ignored. So we have to know. You've got to tell us.
Well, I will tell you. Okay. Well, yeah. but on the topic ignored, it's either ignored or suppressed.
Okay, that's our second favorite topic after ignored.
Well, I'm right with you on that, and in fact, I'm composing an article right now that deals with a kind of repression that scientists have experienced over the years, and 500 years ago, it used to be burning at the stake. So this guy Bruno in Rome, the Catholic Church didn't like his idea, following Copernicus, that it was actually the sun that was the center of the solar system, and not the Earth, and a few more heretical remarks. They took him, they tied his tongue, they stripped him naked, and they burned him at the stake. That doesn't happen anymore, but it's almost equivalent. So there are other scientists, who experience. One of my favorite ones is a guy named Semmelweis. I don't know if you know about his work. So he was a young Hungarian physician, and he got to work at the most prominent hospital in all of Europe, in Vienna. And he went in, and the first thing he was exposed to the maternity ward, and he noticed that the women who came in about to deliver, they were triaged. Some of them went to the midwives, and some of them went to the doctors. The ones who went to the midwives did fine. The ones who went to the doctor, many of them came out in coffins, so it was really a serious issue. And so Semmelweis tried to find out what was going on. This was pre-Pasteur, so people didn't know about so-called germs, and
Yeah.
bacteria, viruses, such. And so he studied the problem and tried to figure out what was going wrong. And he noticed that the routine of these physicians in the obstetrics ward, they would begin their day by examining the women who had died the night or day prior.
Uh-oh.
And then they went right on to do internal exams of the women who were about to deliver. They didn't know about bacteria or anything like that, but he surmised that there must be something wrong with that, and so he started washing his hands. And he found that if you wash your hands, this doesn't happen if your hands are clean. So he brought this to his colleagues, and a naive person would presume that he would get all kinds of accolades for having determined what the issue is, but the colleagues didn't react that way. These people have egos. They were the most prominent physicians in all of Europe, and instead of following his suggestion, which would have been normal, they decided he was crazy, and they sent him to an insane asylum where he died soon after.
Wow.
Oh my goodness.
So that's interesting. Yeah.
Wow.
I mean, that's actually not to go off on a rabbit trail, but that's a concept that's even biblical, to wash your hands. And so and this is before Pasteur had wrote the theory of germ disease. And so that's interesting that he found this, and wow. So Dr. Pollack, this censorship thing, I mean, it's been going on for centuries. And I think it was Ernst Planck that said science progresses one funeral at a time.
Yeah.
And it just takes so long to get some of these other ideas considered,
Well, we need funerals more often, I guess, or something like that.
Yeah. Because what I've seen with your work is these are experiments that you can see this happening, at least with water. And so you look at water, and water's in the cell, and that would be a pretty efficient power source, it seems like to me. And it could be the things that I think you might have alluded to, Dr. Pollack, that, things like protein folding and the other mechanisms that need energy to make that stuff happen.
Well, yeah. I mean, we don't know if it's ATP that, as I said, maybe it is, maybe it isn't. It really needs to be followed up with modern techniques, but it is definitely a power source, and it's there. And usually, Mother Nature, if she's got a power source, she's going to use it. She's not going to dump it or something like this. So I think actually that yes, it is used. And returning to the other theme, it's a pervasive theme that scientists with revolutionary findings, they're either ignored or they're shot down by people. And the established people, they've got the numbers. So if you find something really exotic, interesting, but it steps on the toes of some of those people, there'll be hundreds of people who will say, "Oh, that guy is a crackpot. Pay no attention," because it doesn't make any sense at all.
Dr. Pollack, the tendency to be repulsed by anyone challenging your orthodoxy, are you saying that the easy water and the energy potential or exchanges that are involved, are you saying that there is evidence, experimental evidence, that that's an actual challenge to ATP? Or are you just saying that needs to be looked into? Is there a relationship?
Well, no, there are actually published papers that did experiments that checked out the Lippmann's idea that the molecule of ATP has a particularly high energy phosphate bond that's used to power, and they didn't find it. It's difficult to say, well, they're right and the original guy is wrong, because it needs to be repeated. It needs to be repeated objectively by a bunch of laboratories to find out. Right, this is at the basis of biology. Where does your energy come from? Every time you speak, it requires energy, and where does that come from?
Yeah. Well, so just by happenstance, Dr. Pollack, and I never would have imagined this would have even come up, but just in my professional life, I work with red light therapy for health and wellness. Red light, 600 nanometer in there. And so it's my understanding that it's been demonstrated experimentally that exposure of living human tissue to red light produces a measurable upregulation of ATP production. That it's been measured. At least that's what I've been told in the paper that I read. I thought proved that, but I've since realized that you can't always say that about a paper. But I read another paper that said that they theorized that the reason exposure to red light produced an upregulation of ATP molecules was that it changed the viscosity of the water in the mitochondria so that the ATP synthase could spin faster. And so they talked about the water. And I'm realizing now they didn't know what the water was, I think.
Yeah, I think in the mitochondria, the water is mostly EZ water. I'll say why in a moment. And if you're exposing it to red light, so red light does produce some expansion of EZ, not as much as infrared light does, but red light does. And the depth of penetration of red light, it's probably larger than infrared. So there may be some advantages to using red instead of infrared. I'm not sure about that, but it's just it's a possibility. So in the mitochondria, if you think about the structure of the mitochondrion has membranes in it that are laid out perpendicular to the long axis of the mitochondrion. So it's just full of these membranes, and these membranes are ideal for building EZ water because you need some kind of surface. You don't absolutely need it, but essentially you need it to grow the EZ water. And if you stick an electrode in the mitochondrion, you find a large negative electrical potential. So I think that what's happening in the mitochondrion is it grows as a source of EZ water. And if you add red light, you get more EZ water inside the mitochondrion. And what's it for? Well, when the cell undergoes some kind of action, when the cell acts like muscle contracts, or secretory cell secretes. When the cell is acting, let's take the muscle cell because I have studied that for so many years. So the muscle can be in the relaxed state, and in the relaxed state, the water is EZ water, is filling the cell. And then what happens is the muscle wants to contract. So a stimulus comes, and what happens is that there's a so-called phase transition. Everything in the cell changes. The water changes from EZ water to ordinary liquid water, and the proteins undergo folding. And that folding of the proteins, together with the destructuring of the water, is responsible for the action of the cell. In the muscle cell, it's responsible for the contraction. And when it's all over, the cell needs to return to its initial condition, like the initially relaxed condition, and it needs to rebuild EZ. Now, if a source of EZ is right there, it can rebuild very quickly, and I think that's what the mitochondria does. It's a source of EZ which the cell can use, or another way of looking at it, it delivers negative charge to the rest of the cell, and we know from experiments that if you add negative charge to water, it'll turn it into EZ water. So I think that's what the mitochondrion does.
So are you saying it's a store of energy?
The EZ is a store of energy, yes.
Okay.
So a thought came to mind that the mitochondria we're taught is like the energy source of the cell, like the power supply. So, I mean, this makes a lot of sense that it would be the source of this power. So, Dr. Pollack, I'm wondering, it sounds like there's obviously health implications with this. You know, we know to be healthy, they always recommend you drink a lot of water. But it sounds like, too, to stimulate this, maybe, why it's advantageous to be outside, get sunlight, and because then you're getting the infrared light. What are your thoughts on that?
Absolutely. Yeah. I think many health practitioners argue that we've been duped by the pharmaceutical companies. They want to protect us from sunlight, cover our bodies with all kinds of lotions and sun blockers and whatever. But in fact, reasonable exposure to sunlight is advantageous. It supplies infrared energy, and we need that infrared energy. And those who have studied it argue, and I'm not sure the basis of those arguments, that it's especially important morning light and also evening light before the sun sets. Exposure 10, 15 minutes at least, both morning and evening, can be good for health. And I think the ancients knew that exposure to the sun was helpful, but we've learned stay out of the sun.
Yes. In fact, there's relatively wide agreement now in the dermatology community that the recommendations for sunscreen have been overdone. So they're at least willing to admit that much. And then, if I remember, being under the sun was widely advocated in the book of Ecclesiastes, wasn't it, Fred? If I remember correctly, almost everything was under the sun. So we should get some sun, I think. And by the way, Dr. Pollack, in the health and wellness realm, red light is often augmented with infrared light for pain, wound healing, a number of different things. So, and a lot of what you say is telling me that. So what I've been taught and what we have thought are the mechanisms for the beneficial actions, we just don't fully understand them. We're seeing them and we can feel them and feel better, but there's more going on than we thought, it sounds like.
If you build on a foundation that's erroneous, every structure will be held up by rubber bands and paper clips and whatever. It doesn't work. And
true.
And therefore, for science, I'm always advocating you go drill down to the most fundamental level and make sure that foundation is really accurate. I've been trying to do that. In fact, I have a book that I've written. It's almost done. I was waiting for some illustrations. It's a book that's about the structure of the atom. And I think that what we've been taught is completely wrong.
So, Dr. Pollack, you're in the right place to say something like that. And then instead of being squashed or told to leave the dais, we want to give you the microphone. Okay. So, and you don't have to tell us the whole book. I don't want to let the cat out of the bag, but please, you've got to expand on that.
Okay. So what we've learned from the time of Niels Bohr, that's more than 100 years ago. It's been 5 or 6 generations since. We've learned that the atom looks like a solar system. You've got a nucleus that contains protons and neutrons, and then you've got electrons in orbitals that circle around the nucleus. The charge of the nucleus, it's got protons and neutrons. Neutrons are neutral, protons are positive. So you've got a lot of positive protons compressed together. And I learned in middle school, I learned that when you have a lot of positive charges together, they repel. And the closer they get to one another, the more they repel. So you try to squeeze those positive charges together. They don't want to come together. And so unless you invoke something, the nucleus will explode. Now, the physicists have noted that, and they came up with something called the strong force. And the strong force is a kind of glue that holds together the nucleus, because otherwise it would explode. The problem is that there's no independent evidence for the existence of this glue. It's an ad hoc bandage, basically, to cover a gaping wound. You must.
You're blowing my mind. Well, this is. I was taught all this in second grade through 7th grade, and you're telling me this may not be.
Well, yeah. There's more. There's more. This is middle school stuff. So the nucleus is positive, right? And you've got the electrons around it, and they're negative. I also learned in middle school that plus and minus attract each other. And so if that's true, it means those negative electrons should be drawn toward the positive nucleus, and the whole atom should collapse into one point. But that can't be. I mean, because if the model is right, it can't collapse to one point because atoms take up space. Any material that you have, uh, consists of atoms that are lined up together, and they're not. They must occupy some space because the material occupies space. So this is another problem. Next problem, if you want more problems.
Yeah,
Oh, yeah,
please.
definitely. I'd like to hear what your idea is on it.
Well, okay. So an electron comes from outside, and the first thing is, where is it going to land? Now we're told that if one of those orbitals has less than the proper number of electrons, the new electron can actually land there. So we're accustomed to thinking of 8 electrons. So if one of those orbitals has 7, the electron somehow knows it's not full and lodges there as the 8th one. Now, how does it know? It wants to get away from all those other charges. So why would it want to be in the same orbital? Why would it not like to lodge in between the two orbitals? But it's not allowed to in the model, you see. Okay, next problem. In the periodic table, most substances at room temperature are solids. About 90% of the atoms, like aluminum or something like this. I see my laptop computer. It's made of aluminum, room temperature. The atoms stick together. So the question is, if you put 2 aluminum atoms or any atoms next to each other, explain how they stick together. So the problem is that each one of these contains shells of these electrons, and they're all negatively charged. And the next atom has shells of electrons, and they're also negatively charged. So how do you take these 2 negatively charged shells and make them stick to each other? It's the last thing they want to do. They want to stay away from each other.
Right, right.
Yeah, they'd want to repel.
Yeah, those are a few of the issues, and you have 2 choices. One is to say, well, let's just sweep these arguments under the rug, and this model's been around for a century, therefore it's probably right. Or you can say, well, I'm not so sure it's right. Let's start all over again, because there are a number of issues that don't sit right, and we've got to figure out what's going on, what's wrong, and such. So that's what I've done. I've come up with another model of the atom, which, if obviously if I thought it was grossly wrong, I wouldn't be writing a book. But I think that the shape of the atom is a Platonic solid, and that includes a cube or tetrahedron, such. And I think most of the atoms are cubes. The cubes fit together very nicely. The problem with the solar system model, one of the problems is that you can't get them face to face. There's always extra space when two spheres come together. There's empty space, and nobody ever talks about what's in that empty space. It's not true of cubes. You can take one cube and put it next to another cube, and they stick. And it actually can be very easy for 2 cubes to stick to one another, because one face of one cube, say, is negatively charged, and a complementary face of another cube is positively charged, and they just stick. And that could go on indefinitely. So that's simple. And
so would your model have the quantized shells, electrons?
No, not at all.
Okay.
No. In fact, the model is stable. That's maybe the main criterion. It has to be stable. It can't explode, and it can't collapse. It has to be stable, because atoms are stable. And the model that I've come up with resembles what happens in a colloid crystal. Colloid crystals are well known in physical chemistry, and they consist of positive and negative charges that balance each other. It's a distribution of positive and negative charges that are stable, because you can have colloid crystals that are stable for eons. Once they're formed, they retain their form. And so I adopted that same principle for application in the atom. And it turns out that if you take the model and think about standard observations, a lot of the observations are very easy and directly explained, whereas with the current theory, they're really head scratchers.
Okay. So, Dr. Pollack, I have one question about the atom, and then I know we have a number of questions from our listeners about water that we've been asked to put to you. But regarding a different model for the atom, if things aren't what we thought they are, how did we split the atom, produce nuclear energy, and detonate a nuclear device?
Well, I discussed that in the book manuscript, of course, and it's actually simpler when you think of the standard model, the one that we all know about. So you split the nucleus splits into two parts, and the whole thing is blasted. Two compounds are formed, two daughter atoms, and so the question is, once you smash the atom into smithereens, how do those new elements, those two elements, form? Because the number of electrons has to match the number of protons. So how does those electrons know the proper number to come back after it splits, to come back to form those compounds? I think that's never been addressed, and there's no logical sense, at least that I could think of, that would explain that. In the model that I'm talking about, basically the atom, it's not the nucleus, it's the atom that splits, and it splits at its weakest point.
Would the energy release in your model, is that demonstrated to be similar to the energy release we saw with actual?
I don't know that, because I never performed the computations. Computations are not simple, because every computation has assumptions and some hidden assumptions. And early in my career, I had some experience with the model, and I realized you could pretty much get any answer you'd like by inputting the right assumptions. And so I'm a little about that. So,
Yep.
So there we are.
And plus, you did want to do that experiment in your lab, or else you wouldn't be here telling us about it.
Well, yeah, that is a point.
Well, so just as a layman, I think, well, how could we have done that if we were wrong about something so fundamentally involved? Something so fundamental about what we were doing. And maybe you're saying it didn't matter that we didn't know.
I can't answer that question, but it's more technology than it is science. Building a bomb it was a huge technological effort. It was not so much a scientific effort. Scientists were assembled at Los Alamos, huge number of competent scientists, and they did what was necessary to make it work. Very little theory was involved.
Yeah, they engineered it to make it happen.
Yeah, they engineered it to make it happen. That's right.
Yeah.
And it worked.
Yep. So, yeah, it kind of reminds me of a quote from Nikola Tesla that has to do with basically, people are spending so much time doing mathematical equations, and yet they're not letting experiments and actual engineering rule the day. I'm paraphrasing, but I think that's what happened a lot at Los Alamos. A lot of engineering was going on. Also,
in the area of quantum mechanics, it's basically pure mathematics, is abstract mathematics. And, in his book on quantum electrodynamics, Richard Feynman, the great Nobel scientist, he said in the preface, well, I start with the foreword. The foreword to his book is written by a colleague, and it says, "You won't understand this, but you have to read it anyway because it's important." And I'm scratching my head. Why should I read it if I won't understand it? And I thought next comes the preface, and in the preface, Feynman would reassure me. He said, "You won't understand this." He said, "And I know you won't understand it because my students don't understand it, and even I don't understand it, and I invented it."
Yeah, he basically said something like, if you claim you understand quantum mechanics, you don't know anything, or you're crazy.
You're either lying or you're stupid or something like this.
Yeah,
so
exactly.
So we're dealing, and I must admit, I had some skepticism because I think of Mother Nature, and And I think of Mother Nature, not necessarily well versed in abstract mathematics. And if Mother Nature, perhaps I shouldn't be talking about Mother Nature given your biblical orientation, but anyway, please excuse me. And then I started reading a couple books, and I about quantum mechanics. I thought, well, everybody knows quantum mechanics must be right, even though there are a lot of issues with it. And then I found this book. It's called "Make Physics Great Again," like make America great again. And he rips the whole thing apart, talking about
Oh boy.
assumption upon assumption upon assumption. You start inventing a number of particles, and then you make a measurement, and you find that with the construct that you have built on all those particles, it still doesn't work. And so in order to make it work, you invent another particle, and then you get a Nobel Prize.
I love it.
This book, it's a must read. I think it's fantastic. Make physics great again.
Well, Dr. Pollack, I'm going to pick that one up. And by the way, that reminds me of the funniest T-shirt of the year contest was won at a farmer's market I was at earlier in the summer, and the guy had a T-shirt that said, "Make gas cans pour again." And so I don't know if you guys have dealt with I don't know if you've had a modern gas can. What they've done to the gas can, Dr. Pollack. Anyway. They could have used some engineering advice. Let me just leave it at that. And so now we want to get to, because we are going to run out of time. We've only got maybe 10 more minutes, maybe a little more. But questions about water, because you know things about water that nobody else knows.
Well,
one of our audience members asked, how does water get up 300 feet up a redwood tree?
There's a process that we discovered, which I think explains it, and it also explains what we never got to about a way in which the energy, electrical energy, is used. So we found in the laboratory, actually, another student found that he would take a tube and a hydrophilic tube, immerse it horizontally in the water. And he found that the water flowed through the tube like through a straw. And usually, if you need a pressure gradient, a pressure difference to make it flow. In the case of the straw, you suck on it. In the case of flow through your artery, the heart is driving it. But there was no pressure difference here because the tube was lying horizontally, and yet flow, and it persisted for a very long time. So we studied that, and we found the mechanism had to do with the following. Just inside the tube, like a ring, an annular ring just inside the tube, EZ formed, and in the core of the tube were the positive charges that get formed. And when the negative EZ forms, positive charges form too, and they lodge in the core. And in the core, so the protons, the positive charges begin to build up. They repel each other. They want to get out, and they'll leave at one end or the other end, depending on, I think, ambient conditions. And once it starts to flow, it takes the water with it, and new water enters the other end of the tube, and it just keeps perpetuating. We've had it going for easily a day and a half without stopping. So when you talk about the redwood tree, to start with, this is the kind of mechanism that's used. And it's the infrared energy that builds the EZ and the complementary positive charges. And so there's actually a driver, and this driver is pushing up in the redwood tree. Okay, so now this is, and other trees too. And this leads to what I wanted to talk about earlier, about the energy that's used in our body coming from infrared energy, which builds EZ. So I went to Russia. More difficult to go these days, but unless you want to get thrown in jail. I which I would like to avoid if possible. Um, so this guy was telling me there's a big problem in the cardiovascular system. This Russian guy, introduced to me by my Russian friend after a few vodkas and such. And the guy says, "There's a problem, big problem." And I since I did my PhD research on pressures and flows, modeling them in the cardiovascular system, I was kind of skeptical of anything this guy would say. He had me convinced in 5 minutes that he was right. So what's the problem? The problem is the red blood cells are bigger than the capillaries. So typical red blood cell is 6 or 7 micrometers in diameter, and the small capillaries, of which there are many, are 3 or 4 microns in diameter. So it's a sort of plumbing problem. How do you squeeze through? So he's telling me you need energy. So I'm reminded of the plunger in the toilet. The toilet gets stopped up. You take the plunger and you push, and it requires energy. So to squeeze those red blood cells, and they are squeezed, you can see videos of blood flow, and they do get squeezed. He said that requires a lot of energy, just like plunging the toilet. And he calculated. He said if the ventricle is fully responsible for providing this energy, the amount of pressure that it would need to develop would be something like 1 million times the pressure that it develops. That would be really high blood pressure. So obviously,
Yeah.
Am I mistaken in that we've all assumed that it is the contraction that produces that? Haven't we always assumed that was the source of the energy?
Yeah, me too. For many years.
But
no,
wow.
and another reason why it can't be, if you look carefully at the literature, which my student has done, you find that there are like a half dozen papers that report that if you stop the heart, the blood flow doesn't stop, keeps going at a lower velocity, which means there's got to be something else that is
Something else.
Something else. Both of those arguments, the one from the Russian guy who said it needs far more energy than could be mustered, and the other one showing that stop the heart and flow continues. So I had the idea immediately when I heard he was giving me a half dozen different hypotheses of what that extra driving mechanism might be. And I'm thinking, hey, we just found in the laboratory that we take a tube and immerse it in the water, and the water flows through it. And all of this is actually driven by infrared energy. So we did tests, and we did tests on chick embryos. And in the chick embryo, the cardiovascular system is very well developed after 3 days of development, but not the regulatory system. So it's a pretty pure preparation. And my student, Zheng Li, studied, and he asked, is the signature feature of our mechanism, which means driven by infrared energy, which builds EZ, is that true in the circulation? So first step, stop the heart, and he confirmed also the flow continues, lower velocity, but it continues. And then test the mechanism that we found in the laboratory, this flow mechanism. So he applied infrared energy, and the blood flow sped up by a factor of 3 or 3.5. And then he removed the infrared, and it went back down to its baseline value. So we concluded that in your circulatory system, and maybe even mine, it's not just the heart that's pumping the blood, it's the vessels themselves are actually contributing.
That's fascinating. So were you able to convince, so this Russian scientist, I guess, he convinced you in 5 minutes? Were you able to convince him of your mechanism in 5 minutes?
It was just published in the past few months, and he doesn't speak English through translation. But the guy who was the translator knows, and I don't know if he told him or didn't tell him. I'm not sure. Unfortunately, getting to Russian now is more cumbersome than it used to be.
Yeah, that's interesting. Okay. So Dr. Pollack, one of our listeners also asked that is there potential in what you've discovered in purifying salt water, because there's so much salt water on the globe, so little water is drinkable.
Well, yeah, I mean, this is a big issue. Pure drinking water and irrigation water. I mean, this is the stuff that winds up provoking wars. So we developed a filter. We call it a filterless filter because it doesn't contain a physical filter. What happens is by the energy from the environment, infrared energy, because of the infrared energy, we can separate or divide the water into easy water that's negatively charged and positively charged ordinary, we say bulk water. And we built a device that does this. The reason it works is that when it separates into easy and ordinary liquid water, all the contaminants go into the liquid water. The exclusion zone excludes. So if you capture the exclusion zone water, you're capturing contaminant-free water in theory, and that's how it works. And we did a few experiments about putting salt water in, and the idea was to think about salt as a contaminant. And what we found in some very preliminary experiments, it seemed to work. Didn't work all the time, but it worked some of the time. And so from that, we think it might be possible to use this device as a desalination device. A lot of work needs to go into it. Like when the light bulb replaced the candle, it took quite a few years before Edison came out with a practical version of such. If this actually works, we think it might work. We're not sure. This could provide a method of desalination that doesn't require huge amounts of energy, which right now desalination requires, and only countries or states or whatever with ample money and ample oil and such can afford it. Otherwise, it's prohibitively expensive. What we're talking about, the energy comes from infrared energy, which is available throughout the environment. So if it works, and we're not sure, if it works, it could be a real breakthrough.
Amazing potential, and certainly more worthy of investigation than the next generation nuclear device. That I'm just going to put that out there. And so, Dr. Pollack, you said that you're not necessarily a religious guy. That might have been before we went on air. But I do want to let you know that I love your idea of dividing the waters from the waters. I love that. And we're never offended by references to Mother Earth here, because we know that the God of Abraham, he has a husband-wife relationship with the city of Jerusalem, and from there he intends to rule the world, the whole world, at some point. So it's no offense taken, and we really appreciate you taking the time to tell us some amazing things about the creation that we never knew. Wow, thank you.
Well, thank you. And may I end with, if you're interested, anybody, take a look at The Fourth Phase of Water, the book. It's very popular, and it's got my son's responsible for the illustrations, professional artists, and so many people have commented on the artwork. So have a look.
Yeah, we have someone on our production team reading your book right now. He was one of, we had some listeners mention you, and then this guy started reading your book. So we're showing it right now on YouTube, and the listeners on the radio, you can go to the website and we'll provide information there, links to your book. And we just pray that your research moves forward. There's so many positive things that can come from this. Do you have a decent research team, or what's the state before we close? I'm kind of curious.
Yeah, we have a team. The team now is a lot smaller than it was, and the limiting factor is getting funds for this. Now, the government agencies, the National Institutes of Health, because we're focusing on health applications. I think the word water is maybe a foreign language to them. They never heard of it. And getting funding for the work we're doing for them is a real challenge. So we have to depend on donations. And we were funded for 4 or 5 years by a wealthy businessman who unfortunately ran into some difficulty, and he just wrote an email to me. He signs his emails, Love, Peter. And he said, this was, how did he put it? The most valuable thing I ever did in my life was to fund us. So we're looking for funding because,
wow, okay,
yeah, we can't do anything without money and
yeah, exactly.
and we have so much more to do and so much that's so interesting, but you can't do it without. You have to pay the people. You have to pay for the supplies and the equipment. Otherwise, you can't do it. So it's now fairly small. It used to be much larger. So thank you for asking.
Well, hopefully we'll help get the word out and continue this research. That's for sure. I know for me, I got to start drinking more water.
We all do.
At my age, sometimes there's a trade-off of how much I drink at night, and if I have to take that break in the middle of the night. But this was so enlightening. I guarantee you, very few people knew about this aspect of water, and just the experiments that you've done. That's really established that this EZ water does exist. I mean, it is there, and there's got to be. We've got to understand it better because there's so many applications that can come out of it. A better understanding of the cell, possibly desalination of water. So many other uses. So, Dr. Pollack, what an honor it was for you to join us on Real Science Radio.
Well, thank you for the opportunity. I appreciate it. Thank you.
Yeah. So, for my co-host, Doug McBurney, and Dr. Gerald Pollack, I'm Fred Williams of Real Science Radio. May God bless you.